Holland, and then moved back to Portugal. Now he's professor at ISEL, and as well a member of our center. So Paulo kindly agreed to speak about his result on liquid crystal today. So as usual, we're going to record this talk. So please mute yourself and switch off your video, and it means that you agree to be recorded by staying connected. So please, Paulo, go ahead. But before, share your screen.
Share my screen, yeah, sure. Okay, thanks everybody. Let's hope I can get this to work. Just a second. Okay, here we are. Right, is this working? Let's go into full screen mode now, and let's hope it all works. Okay, very good. Is it working?
Yes.
Okay, excellent. Right, so good morning everyone, and it's my pleasure to talk to you today. And I'd like to tell you about some work on liquid crystals, or more precisely models of liquid crystals, very simple models of liquid crystals, because that's all I can do. Anyway, the full title of this talk is Ordering of Oblate Hard Particles. Oblate means flat. We'll be looking at particles that are disc-shaped, or if you like, pancake-shaped, which is a slightly unusual model for liquid crystals because, as we will see in a moment, most models of liquid crystals contemplate elongated rather than flat particles, but more on this soon. So this is me, Paulo Teixeira, and these are my collaborators, Candy Young-Tilbeck, who did the simulations. I did the theory, and our colleague and friend Doug Cleaver from Sheffield Hallam University. And Candy is a former student of Doug, and I enlisted the help of both of them for this work, which was done in collaboration over most of last year. It's now been published, and it was funded by a grant from Lisbon Polytechnic Institute. Okay, so here are all our beautiful logos. So let's see if I can advance. Hello, this isn't moving. How do I go forward? Wait, this isn't moving. Okay. Right, so first a few generalities about liquid crystals for those of you who may be a little less familiar with them. A liquid crystal is a phase of matter, as many of you know, that is intermediate between a solid, which is fully ordered both positionally and orientationally. So in a crystalline solid, all our particles are at fairly fixed positions and assume fairly fixed orientations. In what's called an isotropic liquid, everything's disordered. So particles point in all possible directions, and they move around so that they occupy more or less all possible positions. And in between, you have what's known as mesophases, or liquid crystal phases, where the particles have various abilities to move, but they all keep pointing more or less in the same direction, which we shall call the liquid crystal director. So these phases are driven mostly by the shapes of the building blocks of the liquid crystal. And typically, liquid crystal forming molecules, so-called mesogens, are either elongated, as is shown here, or they're flat, disc or plate shaped. So what are liquid crystals actually made of? So the building blocks of liquid crystals can be very many different things. They can be molecules. They can be molecular liquid crystals, in which case the building blocks are typically elongated molecules like the one you see schematically here. Or they can be colloidal liquid crystals made up of minerals. They can be made up of viruses. No, not the one you may be thinking about. That one is not a liquid crystal. That's actually a pachycolloid, but that's a different story. All these are of elongated shapes, but you can also have liquid crystal-like structures, which are made of flat particles, such as red blood cells. And even soap if you mix in a little bit of water, can give you a liquid crystal. That slimy, disgusting stuff that you get when you have a bar of soap lying in a bit of water is actually a liquid crystal, although a smectic, not a nematic, as we will be concerned with in this talk. Now, liquid crystals aren't all alike. There are several different liquid crystalline phases, which I show here schematically. These aren't pictures of real liquid crystals. They're pictures of simulations of liquid crystals using model particles, which I think are, excuse me, spherocylinders. Now, a spherocylinder is a model for a liquid crystal that looks like that. It consists of a cylinder capped at either end with a hemisphere, and it's a very popular model with simulators. So you see here a simulation of a crystalline solid. All your particles are neatly arranged into layers. They all have a high degree of positional order, and they all point exactly the same way. Now, if you dilute this a little, that is, if you go down in density a bit, what you have is a bit of disorder. Or equivalently, you go up in temperature a bit, although in the case of hard particles, temperature is irrelevant, but the effect is equivalent. So if you raise the temperature or if you decrease the density a bit, what you have is a slightly more disordered phase where you can still sort of see some layering here, but it's not as well defined as in the crystalline solid. But you still have a lot of orientational order in that your particles still all point more or less in the same direction. If you keep diluting or if you keep raising the temperature, then you get more and more disorder. I forgot to say that this still very ordered but not crystalline phase is the first of our liquid crystalline phases, and it's called a smectic. Smectic comes from the Greek word for soap, incidentally. Now, if you go, as I was saying, if you go further down in density or further up in temperature, you get an even more disordered phase. Now, you don't see any well-defined layers anymore, and you have what's called a nematic. And the nematic is characterized by the occurrence of just orientational order. Your molecules still point more or less in the same direction, but you don't have any positional order anymore, in the sense that you don't have any well-defined layers anymore. And finally, if you go on and dilute even further, or if you dilute even further or raise the temperature even further, and you see there are some voids here which only appear if you have a fairly low density, then what you have is a total disorder. Particles just are all over the place and they point in all possible directions, and this is the usual isotropic liquid phase. Thanks to my colleague Martin Bates for these unpublished pictures to very neatly illustrate the main phases. There are actually more liquid crystalline phases than these. There's more than one type of smectic and there's more than one type of nematic, but these suffice for our purposes. Okay, so next. Now, why study liquid crystals besides their intrinsic interest as a disordered form of matter? They also have many interesting applications. You're probably staring at one such application right now, which is particularly relevant in these times when we spend a lot of time looking at screens. So many of us, perhaps most of us, or perhaps even all of us, will be staring at a liquid crystal sandwich, a liquid crystal between two aligning plates. These are the outside and the inside of your screen, and in between you have molecules of a liquid crystal which are typically elongated with a specific arrangement such that they either let light in and out if in this configuration. That's the off configuration, when your liquid crystal display is transparent, or do not in this particular configuration. That's the on configuration, when your liquid crystal display is opaque. And the result, of course, is spectacular devices such as these, which allow you to look at pretty images and even attend seminars like this. These, as I say here, underpin the workings of what's called the LCDs, liquid crystal display screens, which are not all screens, but a large fraction of them in operation at the moment. So this is one liquid crystal, one particularly important application of liquid crystals, which is as display devices. As I say here, they're used as light valves, which allow light to go in and out controllably by turning on and off a certain voltage. Liquid crystals also occur in many biological contexts, such as the membranes of living cells, which are basically orientationally ordered structures. So if you like, they're like symmetric bilayers. And of course, one needn't emphasize the importance of cell structures. Basically, without this particular form of liquid crystalline alignment, none of us would be here now, and there would be basically no life. So I will not go any further into the biological relevance of liquid crystals. That would be a different talk and for a different to be given by a different speaker, but suffice it to say that they're pretty much everywhere, inside and outside us and other living beings. And finally, liquid crystals are also beautiful. So one of the advantages of working with liquid crystals, or especially if you have friends who are liquid crystal experimentalists, as I am fortunate to be in that situation where I work closely with people who are liquid crystal experimentalists, then you get to see beautiful pictures such as these. This is what's called the Schlieren texture of a nematic liquid crystal. And well, I think you will agree this is aesthetically very pleasing. So that's one of the another advantage of working in this field. Besides pure intellectual stimulation, you can also see some beauty. Well, as I said before, most liquid crystals, or well, at least most liquid crystals that have been studied to date, are made up of elongated building blocks, either molecules or colloidal particles. But, well, that's most of them, but certainly not all of them, because they can also be made of flat objects, such as planar molecules, such as this. And then what do? Well, instead of aligning all parallel to each other, their particles will instead pile up. They will pile up like disks or plates. So some of the faces are still the same. Will still have a nematic face. Now a nematic face will mean not this. It will mean something like this. You pile everything up, no positional order, but the normal directions to each of your plates will all point more or less in the same direction, and that will be a nematic face of disks. And instead of a smectic, which would be layers of elongated particles pointed just like that, instead of a smectic, in the case of these so-called discotic liquid crystals, you can get what's called a columnar phase. That's when they all point not just in the same direction, but they are also piled up neatly like a stack of books. I won't have much to say about discotics or smectics. This talk is mostly concerned with what happens when you have nematic phases, but still it's good to know that all these different phases exist. Okay, so here I show a few examples of molecules that may give you these so-called discotic liquid crystals. Now, why study discotic liquid crystals? Well, first, sheer intellectual curiosity. It's something that hasn't been looked at much before, but they also appear to have a number of interesting properties. So it's useful to know how they behave, and in particular how they behave in confinement. What do I mean by confinement? I mean something like this. What happens when your liquid crystal is sandwiched between confining plates, which I shall refer to interchangeably as walls or substrates, because this is the geometry that occurs in most applications. Typically, you use a liquid crystal sandwich. You confine your liquid crystal between two plates, which have an aligning effect on the liquid crystal molecules or colloidal particles. Because, well, as I said, in a liquid crystal, the particles point more or less in the same direction, but which direction this is entirely up to the liquid crystal to decide. So in practical devices, what we do is we confine them between walls or substrates which have an aligning effect. They break the symmetry of they break the symmetry of orientations. They impose a particular direction in which the liquid crystal molecules all point. This effect is called anchoring, and much of this talk is concerned with precisely modeling the effect of anchoring on liquid crystal particles of the disk-like variety. So coming back here, just to list a few applications, possible applications of Discotic liquid crystals that make them potentially interesting. Apparently, many of them have semiconducting properties and therefore are useful from the point of view of making transistors and diodes and other photovoltaic devices. And they also appear to be rather good lubricants. And this has something to do, it is believed, with the fact that you have a phase that if you have a phase that consists of a disc or disc-shaped particles, they can slide over each other very easily, and therefore give you good lubricating properties for your substance. Right, so it makes sense to model these substances, especially in the confined environments, as I said, that occur in many technologies. This is a nice review article. Well, it's already a few years old, but it's still pretty much on target, that you can review, that you can read on the specifics of Discotic liquid crystals, and in particular, what kind of mesogens will give you this type of phases. But, well, being theorists and simulators, my colleagues and myself are mostly interested in finding some simple model to describe Discotic liquid crystals in confinement, and that's what I shall move on to next. Right, so as I said before, most liquid crystals are modeled, well, often liquid crystals are modeled as liquid crystal forming particles are modeled as ellipsoids. And an ellipsoid can either be something that's elongated, roughly the shape of a rugby ball, that's called a prolate ellipsoid, or it can be squashed, flat, pancake shaped, and that's what's called an oblate ellipsoid. We don't actually deal with true ellipsoids. We deal with a theoretical approximation to ellipsoids, which is called the hard Gaussian overlap potential. This is basically a hard particle model. So the interaction between two such particles is zero if they don't overlap at all. If any part, however small, of them overlap, then this potential is infinity. So what this means is that these are particles that just bump off each other and don't ever overlap. And the potential is specified in terms of this quantity here, which is the distance of closest approach between two particles. So what it's telling you here is that if the distance between the two particles is such that they overlap, then they don't want to do that. Otherwise, it's 0 and they don't even know about each other. All they do, therefore, is bounce off each other. And this distance of closest approach, that's the minimum distance that two particles can be apart when they're just touching. And this is, of course, a function of particle orientations as given by this vectors omega-1 and omega-2. So, of course, how close apart they can be will depend on whether they are oriented, say, like that or say like that. But it will also depend on whether they're like that or like that, which means that this distance to closest approach also depends on R12, which is the vector, the unit vector, along the direction connecting the centers of two particles. And the key parameter in this formulation is this parameter we call kappa, the particle elongation, which is the ratio of the long to the short axis of your ellipsoid, where sigma L is the long axis and sigma naught is the short axis, or more precisely, that's right. This is the long axis, that's the short axis. So this is known as the particle elongation, and particle elongations greater than 1 means your particles are prolate, they're stretched out ellipsoids, and if it's less than 1, then your particles are oblate, and your particles are just flat, like pancakes. And in addition to this, this is what particles are. Now we need to sandwich them between surfaces. And what are we to make of that? So this is our model of a surface. Here is our particle. And what's this little thing inside our particle? Well, it's actually difficult and perhaps not always transparent to model the interaction of one of these particles with a surface. So we come up with a simplified model which consists of the following. Take our particle. This is a pancake-shaped ellipsoid. Now imagine that two particles see each other as ellipsoids, as given by this potential that I described before. But when it comes to a wall will see a particle not as a full ellipsoid, but as a disk. A particle will see an ellipsoid not as an ellipsoid, but as a disk embedded inside the ellipsoid, located halfway along its, in this case, short axis, and perpendicular to it. So a wall sees a particle as as an infinitely thin hard disk embedded inside the ellipsoid, perpendicular to its short axis and placed halfway along it. And now the diameter d of this interior disk need not be the same as sigma naught, the full diameter of the ellipsoid. And this is the potential that describes what I've just said, that the wall excludes not the full ellipsoid, but only this inner, infinitely thin, hard disk. And now, by playing with the diameter of this inner disk, we can tune the anchoring properties of the wall. So it's not difficult to imagine that if d, big D, is almost the same as sigma naught, the actual ellipsoid diameter, then the wall will exclude most of the ellipsoid, and then what happens is the ellipsoid wants to sit parallel to the wall. Parallel meaning in this case that its short axis points perpendicular to the wall, and the plane of the ellipsoid is parallel to the plane of the wall. So we have in this case what we call face-on alignment, but homeotropic anchoring, because the perpendicular, the axis of symmetry of the ellipsoid is perpendicular to the wall. On the other hand, if this D is small. So if this disk is very much shrunk, then the ellipsoid can sort of point in many different directions relative to the wall. It can embed most of itself in the wall as shown here. And what happens is the disk, the ellipsoid, will tend to align itself edge on, perpendicular to the wall, but with its short axis parallel to the wall, its axis of symmetry parallel to the wall, giving what's called planar anchoring. And most importantly, D, big D, doesn't have to be the same. If you have what's called a slit geometry, that's a liquid crystal sandwich between two parallel walls, you can choose D to have one value at one wall and a different value at another wall, so you get different types of preferential alignment at either wall. The anchoring, or I shall use the words anchoring and preferential alignment as more or less synonyms. So what this means is that you can have situations where you have particles that want to be face on at one wall and edge on at the other wall, and this gives you what's called a hybrid film, which I shall come back to in a moment. In the simpler case, where these at either wall are such that the preferred alignment is the same, then you have what's known as a symmetric film, and all varying degrees in between. So now a few words about theory. I'm afraid I have to show some ugly formulae now. So what we do is we use something called density functional theory, which basically allows you to write the free energy of your system. And because your system is going to be non-uniform, if you put this model between two walls, you will have a density that varies from one point to the other throughout the film. So your free energy is not just a function of the density, because the density is varying from one wall to the other. It is a functional because it depends on the density at every point. And these being non-spherical particles, as I said, they're oblate ellipsoids, the free energy will depend not just on the density, on how many particles you have in any infinitesimal volume element at every point between the two plates, but also on particle orientations, on which way the particles point. Because, well, if you have your particles all pointed in one way, you will be able to move more freely. You will be able to, as it were, maximize your translational entropy. But if you have particles moving in different ways, they keep bumping into each other. Okay, so if they all point in different ways, they will maximize their orientational entropy, but they will have little translational entropy because they can't slide along as easily. So you have to put all these ingredients into your theory, and the formalism of density functional theory allows you to write down the free energy of your system. Let me just go briefly through what we have here. This is the first ideal gas term, and then you have this second term that takes care of the interactions between one particle at Z1 with orientation omega-1 and one particle at Z2 with orientation omega-2, where Z we take as the direction perpendicular to the plates. We shall be considering, as I said, what's known as a slit geometry, where you have two parallel walls and the liquid crystal in between them. The walls are perfectly flat, unstructured and parallel, unstructured except for the fact that you can tune their degree of permeability by varying this D parameter, the diameter of the inner disk that I just described. And this is something that describes the excluded volume interaction between two ellipsoids. This is the wall potential that I just showed you. That's the chemical potential. And this is, well, this is basically a correction to take into account the fact that what I'm doing here is too simple a theory. This is just Onsager's second virial theory for those in the know. And Onsager's second virial theory doesn't do too well if your particles are either not elongated enough or not flat enough. So what I'm doing here is I'm trying to fix this simple theory by just multiplying by some prefactor which attempts to correct for the fact that Onsager's theory only goes up to the second virial coefficient and not up to infinitely many virial coefficients, as it should if it were an exact theory. Excuse me. Right, so, well, what do physicists do? Once we have a free energy, we minimize it to find equilibrium. And what does this give us? Well, it gives us what's called the density profile. What's the density profile? The density profile tells you what the density is at every point in the region between the two walls. And it's just a function of a single coordinate which is measured perpendicular to the walls, the z coordinate as I've just described. And this is the integral over orientations of this rho z omega, which appears here in your theory. And besides that, we also have another set of parameters called the order parameters, which tell us which way particles align relative to our reference frame. And the simplest one, which we shall be dealing with mostly in what's to come, is what's called QZZ, or the average of P2, P2 being the second Legendre polynomial. And basically QZZ tells us how strongly aligned the short axis of particles are along this z-axis. So a positive QZZ, remember these are flat particles, so your z-axis goes like that. A positive QZZ means the particle is like so, aligned parallel to the surface, but with its short axis parallel to the z direction. A negative QZZ means the particle is like that, with its edge with its edge towards the surface, so edge on alignment. This was face on alignment, and its short axis parallel to the surface. So QZZ means this, face on alignment. QZZ, so positive QZZ means this, face on alignment. A homeotropic anchoring, as it is known, particle lying flat on the surface. Negative QZZ means this, planar alignment, planar anchoring, edge on alignment of particles. And everything in between. Of course, you can have all different values in between negative and positive. So moving on. This other parameter attempts to measure what's called biaxiality, meaning, is there another direction of alignment? Do we have the simplest kind of order where we have order along only one direction, or is there a secondary director? Is that some other direction along which there is also order? And in particular, if your particles are aligned along the substrate, is there a perpendicular? Do they all want to be parallel to each other in any direction in the plane of the substrate, or is there a preferred direction in the plane of the substrate? And that's measured by this other order parameter. And especially in the case of hybrid films, that is, when anchorings are different at either wall, as we shall see in a moment, it's useful to also compute this so-called total order parameter, which tells you, well, how much order there is in all possible directions. These Q entries are just the entries in the order parameter tensor as is usually defined. Those of you who are familiar with say Landau theories of liquid crystals will recognize them as such. And if you want to really understand what these order parameters are about, you should go to this paper here and look up this figure. This is figure 2. This is QZZ, also known as eta, or the average of P2, which tells you how much order there is in the Z direction perpendicular to the plates. And this one is our QXX minus QYY, which tells you if there is order in a specific direction parallel to the walls. Okay, so much for theory. Now some details of simulations. My collaborator Candy Anktil-Dek was able to do some NVT Monte Carlo simulations of 864 particles. She simulated the bulk systems for a range of particle elongations, all given here. You'll see the phase diagram in a moment. And then she also simulated the confined system for the specific case of ellipsoids of elongation 0.345, sandwiched between two substrates, a distance of 6 sigma naught, that's 6 particle diameters apart, along the Z direction, and periodic boundary conditions along the transverse directions. And these are just some details of how the NVT simulations were done. We can come back to this if anybody's interested, but now I'll move on to some results. Well, these are results for the bulk order parameter, the P2 of a bulk system for different elongations. Elongations decrease, kappa decreases from left to right. So, and the symbols are from simulation. The lines with no symbols are from theory. So you see that theory predicts correctly that there is a jump of the order parameter at a given density, which means the isotropic to nematic transition is first order. In simulations, there are always finite size effects, so the order parameter doesn't quite get down to 0, and its jump isn't quite discontinuous. So what we see here is that what we are seeing here is that basically our theory is predicting that the isotropic to nematic transition is delayed to higher densities than is seen in simulation. And this can be systematized in the following phase diagram. This is a complicated phase diagram. I'll tell you what's on the right half. In the right half, you have earlier results by ourselves and others for prolate ellipsoids. That's kappa greater than 1. And in the left half, you have the present results for oblate ellipsoids kappa less than 1. The full black lines are from theory. The symbols are from simulation. And you see that there are two sets of simulation curves here. These are the curves for the nematic isotropic coexistence, determined by two different methods. And what you already begin to see is that, well, the agreement between theory and simulation for prolate ellipsoids is substantially better than in the case of oblate ellipsoids. Okay, this we believe, and this is an effect that's been somewhat already discussed in the literature, the fact that in the case of oblate particles, the higher order virial coefficients that are being neglected in the theory carry considerably more weight than in the case of prolate ellipsoids. So moving on now to the structure of our confined films, we start with a symmetric film. That is same anchoring at either substrate. So the film is perfectly symmetric. ds is just the diameter of the inner hard disk divided by the diameter of the full diameter of the ellipsoid. So 1 means that the disk has the same diameter as the full ellipsoid. And again, these are the top panel is the density profile, the middle is QZZ, and the bottom panel is this biaxial order parameter QXX minus QYY. And the curves, black is a density in the isotropic bulk phase, red in the intermediate region, in the intermediate interface region, density intermediate between that of the bulk isotropic and nematic phases, and blue is definitely deep into the nematic phase. And these curves, these three curves in the top panel have been shifted by some arbitrary amount to make them visible, otherwise they would be on top of each other. And in this case, alignment is face-on, homeotropic. You see, it's not too bad, actually. Theory doesn't do too bad in this case, especially at the lowest density, it's very good, but or pretty good, actually. But even at the highest density, it isn't bad. And this applies to the density, applies to the main nematic or the parameter QZZ. And of course, we predict that in this case, there is no biaxiality because, of course, well, all particles just want to lie flat onto the solid surface, and there is no other preferred angle. They can rotate whichever way they like in the plane of the surface. Now we go to the opposite extreme. The opposite extreme, that's a zero inner disk diameter. So now the disks are allowed to rotate, and what they want to do now is to align edge on. They want to stick half of themselves into the surface. These are purely entropic effects. Remember that all we have here is hard body interactions. And here we see that, well, at low temperature, at low densities, the theory still does well, of course, but if you go up in density, then things start to go awry a bit. You still predict a fairly strongly layered structure, but we're getting the number of layers wrong. This is for the QZZ or the parameter. We predict the correct type of alignment, that's edge on to the wall, but the amount of order that we predict is less than what's seen in experiment. However, we do predict correctly that there should be some biaxiality. Of course, if you have a stack of layers aligned edge onto the surface, they want to take up some specific direction. They want to take up some specific direction in the plane of the surface. They don't want to point in all different ways. Although that's exactly what you see if these 0.5, the diameter of the inner disk is half the diameter of the actual ellipsoid, then you predict that there should be biaxiality, there should be a preferred direction in the plane of the surface, but theory doesn't show you that. And we believe that this is probably because, well, if you have now looking at the plane of the surface, what we believe is happening here in the simulation is that the preferential direction in the plane of the surface is actually jumping from one simulation step to the other, and therefore we end up not actually seeing order in the plane of the surface. But still, even in this case, the theory is still predicting qualitatively correctly that the anchoring should be planar, that is, that alignment of particles to the surfaces should be edge on, as reflected in the negative values of this QZZ or the parameter. Again, the number of layers we predict for the density is incorrect. Now, what we don't predict correctly, however, is when you cross over the value of the S for which you cross over from face on to edge on alignment. For 0.55, theory still predicts that alignment should be edge on, that is planar anchoring of the disks, but simulation already gives you face on alignment. So we don't get this crossover quite right from our theory. We're a bit off, not terribly off. I think it's 0.6 we find where the two, the prediction again gets fulfilled, but still it's not as perfect as it's not as accurate as we would perhaps like it to be. If we go up to 0.7, then things go better again. We again predict the correct type of anchoring. See again here, density, QZZ, QXX minus QYY, of course no biaxiality in this case, because now we have homeotropic anchoring again. Some pretty pictures for the 4 inner disk diameters. Density increases from left to right. So this column is a density in the isotropic bulk phase. This rightmost column, the leftmost column, is a density in the isotropic bulk phase. The rightmost column is a density in the nematic bulk phase. The bounding plates, the bounding surfaces are actually at the top and bottom surfaces, and blue means face on, so particles lying on the plates with their short axis perpendicular to the plates. Red means red, or yellow means edge on, that is that is the minor axis of the particles lying parallel to the plates, the particles sticking edge on into them. Okay, so here you see for the larger ds, you see particles all pointing like that, and in this case you see particles all pointing like that, and here a situation which is more like this, but somewhat less ordered. Now moving on to hybrid films. Now these are different at either film, and what we're looking at here is the average total order parameter that we saw before, because now QZZ will change sign from one wall to the other. If one wall wants to induce face-on anchoring and the other wants to induce edge-on anchoring, then you have a change of sign and it gets a little difficult to interpret. So what we have here is basically the trace of the squared order parameter tensor, again as a function of density. And we again begin to see that, again, theory does not predict a rise in this order parameter until a higher density than is found by simulation. However, the theory does predict that there will always be some biaxiality. Sorry, I forgot to say, these curves are for different pairs of d values at either wall. So some of them, green for instance corresponds to the maximally hybrid structure where you have d of 1, so perfect face-on order at one wall, and d of 0 at the other wall, so that's perfect edge-on order at the other wall. Still, we predict that, theory predicts that the curves that you will always have some biaxial order, except of course when these are not too different, and then you have effectively not a hybrid film, but almost a symmetric film. Densities, maximally hybrid case. Well, this is a lower density in the bulk isotropic region, intermediate density, and then one in the bulk nematic region. So you see that, well, things are not going terribly well here, and theory is not as good as predicting the density as it was in the case of a symmetric film. And the same thing for the orientational structure as described by the order parameter. What we see here is the top panel is now the lower density, the middle panel is the intermediate density, and the bottom panel is the higher density. And we see that at low densities, our predictions for both the total order parameter, QZZ, and the biaxial order parameter are pretty good. But at the intermediate density, we're not doing too badly, but things go a bit wrong at the higher density, and we basically don't predict the correct structure. Here, theory would predict the film to be mostly edge-on, mostly planar ordered, with a bit of homeotropic order near the homeotropic wall. Simulations give you a linear variation, which means that the orientation varies continuously from planar at this wall to planar or edge on at this wall to perpendicular or face on at the other wall. Okay, so I won't bore you with lots of results for hybrid films because, well, what we see here is that, well, simulation isn't doing great already at intermediate densities. Although in the cases where these at either wall are not, the two walls are not too different, we still get qualitatively correct results. So what I show you now is a synthesis of our results from simulation. These are the inner disk diameters at the bottom and top walls. Of course, the diagram would be symmetric with respect to this diagonal, so I only show half of it. These are the regions for which you get uniform planar, that's uniform edge on, uniform homeotropic, that's uniform face on, and the linear variation from one to the other, depending on what values of D you choose at either walls. And these are configuration snapshots, which are typical of each of these different regions. More snapshots. Again, here you see clearly in this one that you're going from face on at one wall at the bottom to edge on at the wall at the top, and you see a fairly continuous variation from one to the other. And that's it really. So I've told you about a simple model for Discotic liquid crystal films that we used a simple theory to describe, and we got results that are mostly qualitatively correct, but somewhat less so in the case of hybrid films. So what we're doing now is we are working on trying to improve the theory, and we're also currently running some simulations on a thicker system in the hope that, well, things might, the predictive ability of the theory might be better for a thicker system than for these very thin ones, because, well, we already know that that is the case when we deal with prolate ellipsoids. Predictions are better for thicker films than for these very thin ones. And with that, I'll thank our sponsors and thank you all for your attention, and we'll stop here.
Thank you, Paulo, for this interesting presentation. Now we have time for discussion. Please, people who have questions, just ask Paulo.
I have one about the theory.
Yeah.
I don't understand why you cannot change the fudge factor to get the number of layers right, because that's a two-body effect. That is not a three, not here. If you just go back to the simplest, yeah, the number of layers that is wrong.
Here,
yeah, yeah. If you change the fudge factor, you should be able to get the right number of layers. The fudge factor is only a fudge factor. You just put something in front of the.
Yeah, well, there is some. I mean, you don't just put anything there.
You put, Paulo. You put. I know. You put anything there. So you can put any fudge factor, and see if this is a two-body effect. By changing the fudge factor, you should be able to fix this. I'm not so worried about the threshold.
Well, I would say that okay, you can possibly do, I believe you can do that, but what worries me most here is not so much that I get the number of layers wrong, it's the fact that I don't...
That's very important. I mean, it's the packing. I mean, getting the number of layers right is kind of either it's right or either it's wrong. It's not so much like the threshold being 0.6 rather than 0.6.
Yeah, no, but what I meant is, what I'm mostly concerned with here is the fact that we can't get this this region at all. We always predict either uniform planar or uniform homeotropic anchoring, but not this linear region, at least for this particular film thickness.
Calculation for that. I mean, you have to.
Sorry, I'm sorry. Can you start again? I missed the beginning.
Yeah, that was another question that I had, and I think you can do a back of the envelope calculation to measure, because that's really what determines whether it's sharp and then flat or whether it goes continuously. or linearly. I mean, you have to calculate the energy, you know, the cost of changing the orientation. I'm pretty sure you can get some feel for that. I'm not even sure the simulation is does not get stuck. It depends. I mean, you have to compare the free energy, elastic free energy of the two interfaces, if you like, or of the two short spaces where it changes, or one, with a very with the free energy, the elastic free energy of doing these. And I don't think the linear thing will always win, because who knows? But that's elastic energy. I'm not sure that's in Onzager you don't have the elastic terms, but you can calculate the elastic constants, and so you can get the elastic energy consistent with your theory. And I bet, you know, if you have any other model, you can do that. And this linear thing is a little bit suspicious to me. It's interesting if it's there, but it's a little bit too, it's a little bit suspicious.
Well, as I said, we are currently running simulations on thicker systems, so we'll see what comes out of that.
Well, it may not even be just the thickness; it might be some kind of intermediate metastable state or whatever.
That is also possible, because one other aspect I've mentioned is we are not quite sure what these white regions in between the different domains mean. Could these be multi-stable regions or whatever? That's something we're also looking at the moment.
But if it is a linear state, true linear state, you should be able to get it from Frank free energy. I'm sorry, I mean you should be able to get two plates and some Frank elastic constants, and then you can check if this happens or not. The simplest macroscopic model. It probably maybe does happen for certain values of the elastic constants. I don't know.
Yes,
but it's a weird. I mean, well, could be there, but it could be an artifact as well.
Well, yes, you're right.
A simple explanation in terms of the elastic free energy, you cannot discard that this is an artifact, and it's not just finite size. It could be finite time. It could be metastable. But I don't want to monopolize this. It's simple arguments will help you to understand the phases, and I think that you're lacking some simple arguments to understand the linear phase, if it exists, and for the number of layers, change the fudge factor. I mean, if you have one fudge factor, you can have any other. When you have ice cream, you can put more fudge, less fudge, no fudge. It's fudge.
Yeah, but you can't add cyanide, do you?
If you cannot get the number of layers right by changing the fudge factor, then I would be very, you know, then it's a very specific three or many body effect, which for layers. Then again, you can check the idea. Where does it come from? I don't know. I have to go. Okay.
Can I just make one final comment on that? You see, one issue with making comparisons with macroscopic theories that ideally you'd need to be able to quantify the anchoring energies, and we really have no easy access to anchoring energies here.
Oh well, but you do have an anchoring energy, of course. Otherwise, it would not go flat or perpendicular.
Yeah, there certainly is an anchoring energy. We just don't know very well how to measure it.
Well, again, that could be a parameter of your simple macroscopic theory. You know, you can use that as a parameter, and maybe for some anchoring strengths, if the film is very thin, I would guess that what in one of the walls is much stronger than the other, then it will be uniform. It'll, we can talk about this.
Oh, well, that's.
We know that from other models, you know, and just from macroscopic.
Yes, I am familiar with that work.
So it's. I think that's what you're lacking. We don't know what this is. If it's just an intermediate state or if it happens for a very particular choice of all the different energies, the elastic, bulk, and the anchoring, yeah, or the difference between the anchoring. But anyway, I'm more interested in seeing the number of layers. One beer, if you can get the number of layers right by changing the fudge factor.
Can you make it a glass of milk?
Well, a glass of water then, anyway. For the linear one, I think you need to think a little bit harder and think of simple models, compare energies, because, you know, computers are, you know, 800 particles is not too much. And we all know the defects of DFT. I mean, it's doing better than we even dreamed of. Anyway, a glass of beer if you get the number of layers right by changing the fudge factor.
Make it a glass of milk, will you?
I don't know, I mean, it's virtual. It doesn't matter. I mean, I'll give you beer, you drink milk. Hey, water. Oh, I don't care. You don't drink anything.
No, I drink mineral water. I drink
Oh,
milk. I actually drink lots of different things.
Paulo, let the others ask questions.
Somebody, go ahead, please.
Yes, so I have a question, Paulo. I think it's somehow related to what Margarita has been saying in the end. So I really don't understand why you have to model the interaction between the particles and the wall in the way that you explained. Isn't there a simpler way to do it?
Such as?
Just as I mean, you have some kind of vector that defines the orientation of your particle, and you could add something that, I mean, it's the interaction between those two vectors and the wall. I don't know why you have to put this disk. I didn't understand why it's simpler to put the disk in the.
No, it's not. It's not. I wouldn't say it's simpler. It's just, yeah. I understand what you're trying to say. Why don't I just postulate some potential, some P2? Is that what you're trying to say?
No, not postulate. So just put something that is simpler, but still retains the thing that you want to model, which is that the wall is not penetrable.
Yeah, P2, like a P2.
The only thing that you, okay, so but that's not even the more important part of my question. The other part is, and I think it's related to what Margarita said. I don't know too much about this, but I always see the anchoring. The anchoring has an energetic part.
Yeah.
And here you only have entropy. So you only have repulsion. So you only have entropy. So why? Aren't you far away from reality by doing this? I mean,
not necessarily. The idea. Well, I can wrap up those two. I think I can wrap up the answers to both your questions into just one. The idea here is to try and make contact with how anchoring is actually induced in real world systems, and the way it's often done is you have some adsorbed layer on a surface, right? You don't have a bare surface, you have some adsorbed layer. And you tune the anchoring by varying the density of that layer, which in real life corresponds to particles being able to embed more or less of themselves into this layer. So the idea of using these potentials is to try and make contact with that particular experimental situation.
Okay, thank you.
But yeah, other people do as you say. You just use some potential that has the right symmetry and gives you the types of alignment that you want.
We're not hearing you, Miko.
Okay,
Miko?
Yeah. Are there more questions? No. Paulo, in the diagram final, is it asymmetric with respect to the reflection? What happens in that upper left corner?
Wait a second. Let's get there. Well, yeah. I mean, if this region here, you mean?
Yes.
Well, that would be just like swapping the two plates. So it would be the same thing. It doesn't matter which plate is top and which is bottom, or which is left and which is right.
When I look to this linear snapshots, do I see it correctly that in the middle of your system you have molecules with director making an angle, constant director?
This one?
No, on the diagram.
Oh, okay. Just wait a second.
On that final diagram.
Here, this?
When I look on the snapshots.
Like this?
Yes, for example, this one. It seems to me that in the middle of your system you have molecules which are all oriented with a director, let's say, in 45 degrees. So
yes, it will be oriented at all intermediate angles from 0 to 90 degrees.
So is the director changes?
Yeah, it changes continuously from one to the other in this linear region.
So and you calculated only QZZ.
Well, I calculate everything. I just showed you QZZ. But you can calculate all other parameters, and I'm just not showing them.
Okay. So do we have more questions from audience? No more questions. Then I would suggest we thank Paulo again for his talk, and at this point we can finish our seminar. Thank you for your presence, and we see.
And we'll be back next week.
Yes, thank you, Paulo.
Okay, thank you.
Paulo, may I just ask you one question?
Sorry?
Can you stay for 1 minute?
Okay. Is there a question?
Yeah, it's more technical, maybe not for everyone. So in those correction factor, Lee, can you go to the formula?
Yeah, just a second. Just a second, I'll get back there. This.
So yes, it's the Carnot-Starling equation.
Yeah.
And then this A prefactor comes from where?
This prefactor comes, well, first it's not done correctly, because if you want to do it a bit more correctly, it should be inside the integral, because this is a prefactor that depends on the density, and it should depend on the local density and not on the bulk density. But this is basically some attempt at resumming, at including the resumming the higher order virial coefficients and including their effect.
And okay, I'll say, and this 8 is related to the oblates.
Well, the 8 is always there. It has to do with how you do the resummation.
And if I would like to do it for the ellipsoids of finite aspect ratio.
Precisely. This will go. I think this will go to 1 if you have infinite aspect ratio, and it's here precisely because your ellipsoids have a finite aspect ratio.
No, but I'm asking, does it matter if you have ellipsoid or oblate?
No, it has the same form whether they're prolate or oblate. You just change the kappa in them. It just goes into here. You see, it goes into here, but it doesn't matter whether it's oblate or prolate.
Because you have and for hard ellipsoids and hard prolates would be the same. Just what would change? Just Meyer function, that one that you.
Yes.
Okay.
But you see, we still predict the theory, even with this correction, still predicts a symmetric phase diagram, you see, whereas in reality, the phase diagram is not symmetric.
Yeah. And you never, and in simulation, you never enter into a symmetric regime.
Well, for oblates, you would not have a symmetric, you would have a columnar phase. But no, we don't see a columnar phase.
Okay.
And this, well, it's doubtful whether you would ever see a symmetric phase even for prolates, because as you know, hard ellipsoids don't give you a symmetric. And well, this may be close enough to ellipsoids that you wouldn't see a symmetric.
So you say that hard ellipsoid will never.
No, hard ellipsoids don't give you a symmetric face. This is well known.
Mm-hmm.
But anything other than any other elongated shape seems to give you a symmetric face. Now the question is this approximation close enough to ellipsoids that you don't see a symmetric face, or is it far enough from hard ellipsoids that you still do see a symmetric face? And I don't think that's known.
Mm-hmm. So you said any other elongated shape like spherocylinder give you symmetric?
Absolutely. Spherocylinders. There's an interesting paper by well, I forget the guy's name now, but where he looked at a continuum of shapes all the way from spherocylinders to ellipsoids. There is a way to parameterize this shape so you can change it continuously. And what he found was that if you can get arbitrarily close to a hard ellipsoid and still get a symmetric face, but when you go all the way to the limit of hard ellipsoids, you lose it.
He did it in DFT.
I think he did it in DFT. Strictly speaking, it may have been, I don't recall all the details, it may have been in the limit of perfect order, which is probably not too dramatic because a symmetric face is very highly ordered anyway.
Okay. Okay.
But I'm trying to remember the guy's name, but I just can't right now. I'll tell you later.
Please send me the name. I find reference or reference.
Yes, it's something from the 1990s. But I just can't remember the guy's name right now. Okay.
Okay, Paulo.
Thank you, Nico.
Bye bye. Have a nice day.
Bye. Thanks.